body. Today we are going to discuss about resolution and its types. Resolution is the ability of an imaging device to distinguish between two closely spaced objects in close proximity as two. Different types of resolution are: number 1, spatial resolution, which is the ability to image accurately the detail or quality of an image. Spatial resolution is dependent on pixels of a monitor and scan lines of an image, and comprises of axial resolution, lateral resolution, elevational resolution. Number 2 is temporal resolution, which is the accuracy of moving objects. And finally, third one is contrast resolution, which is the accuracy to differentiate between different shades of gray. We will study them one by one. Axial resolution refers to the ability of an ultrasound system to distinguish or differentiate between two objects that are close together along the path of the ultrasound beam's propagation. These objects lie one behind the other, or along the main axis of the sound beam. Axial resolution is critical for producing clear and accurate images of the structures being examined. The main determinant of axial resolution is spatial pulse length, which is the length of one pulse of sound energy emitted by the transducer. Axial resolution is half of spatial pulse length. Therefore, shorter the spatial pulse length, the better the axial resolution. Higher frequency transducer provide better axial resolution because they have shorter wavelengths and thus shorter spatial pulse length, allowing for more detailed imaging. As we have studied, that the two objects can be clearly differentiated as two when their separating distance is greater than half of the spatial pulse length, or axial resolution. If the distance is smaller than half of the pulse length, that is less than axial resolution. The two objects cannot be resolved as two during US imaging. On the left side of the following image, each of the reflector must be at least 5 mm apart, or more, to be displayed accurately as spatial pulse length. If 10 mm, and half of 10 mm is 5 mm. If less than 5 mm, machine displayed them as 1. On the right side, spatial pulse length is 2 mm. So each reflector must be at least 1 mm apart. If we compare the two center view, the image on right side has better axial resolution than B because of less numerical value number. Axial resolution is the best measure of spatial resolution. Lateral resolution refers to the ability of an ultrasound system to distinctly identify and separate two closely spaced objects that are at the same depth and position side by side, that is perpendicular to the sound beam's main axis. It determines the system's capacity to resolve structures that are adjacent to each other in a plane perpendicular to the beam direction. It is the minimum distance or minimum separation of two structures positioned side by side and still can be seen apart and produce two distinct echoes on an ultrasound image. Lower is the numerical number, better will be lateral resolution, and more accurate image will be if space between two reflectors is less than lateral resolution. They will not be resolved and seen as one structure. If space between two reflectors is greater than lateral resolution, they will be resolved and seen as individual structures. The main determinant of lateral resolution is beam width or beam diameter. Narrower the beam, better the lateral resolution. If the distance between two adjacent reflectors is less than the width of the ultrasound beam, They will appear as a single object. Lateral resolution increases when the distance is greater than the beam width. Primary method of improving lateral resolution is focusing. Lateral resolution is best at beam focus. Elevational resolution concerns the resolution in the third dimension. That is the thickness of the imaging slice, which is perpendicular to both the axial and lateral dimensions. It refers to the ability of an ultrasound system to distinguish between two objects in the imaging plane's thickness, or the slice thickness of the ultrasound beam. Elevational resolution is dependent on the height of transducer element, in much the same way that the lateral resolution is dependent on the transducer element width. The height of the transducer element determines the thickness of the ultrasound beam. In the elevational plane, a smaller height leads to a thinner imaging slice, which improves elevational resolution. Higher frequency transducers and focus beams can enhance elevational resolution by narrowing the slice thickness.